In exercise 2.5, we just don't meet an ordinary entrepreneur, but we meet an enterprising entrepreneur. And this is not because of the things that he does produce, because he only produces these very boring widgets, but it is because he purchases not one, but two firms to produce those widgets. And that makes the entrepreneur enterprising and the exercise interesting. So each of the two firms produces the identical products, widgets, and each has a production function given by something that you recognize as a Cobb-Douglas production function. However, the firms differ in one dimension, which is the amount of capital that they have in place. And firm 1 has 25 units of capital in place, and firm 2 has 100 units of capital in place. And the rates of capital and labor are given by the very simple W is equal to V is equal to 1. Question A is, if the entrepreneur wishes to minimize the short-run cost of widget production, how should he allocate output between the two firms? And the two firms differ in the amount of capital that they have in place. So this is what is given in the exercise, and now we need to come up with the short-run cost function. Now let's first focus on firm 1, which has 25 units of capital in place. So in the production function that is given, we can replace the k here with 25. So we get square root of 25 times the square root of L1, which is equal to 5 times the square root of L1. And now we solve for L1 in order to get a contingent demand for labor. And because we have the rates fixed at 1 W and V, on the right hand side only the output, the Q, appears. So solving for L, we get the contingent demand for labor as a function of V, W, and Q, but V and W are fixed at 1. So this gives us the expression Q1 squared divided by 25, meaning that if we plug in a certain output level at plant 1, then we get the number of units of capital that need to be hired in order to attain that production level. We can do the same for firm 2 or plant 2. So, but there 100 units of capital are in place, so the K gets replaced by 100. Doing the same derivation, we get the contingent demand for labor at firm 2 being equal to Q2 squared divided by 100. And here, of course, it's important to distinguish between the production at plant 1, Q1, and the production at plant 2, because they may be different. Now we have the labor as a function of the output, and that enables us to derive the short-run cost function, because the short-run cost function is number of units of capital in place. So this is the short-run cost function for firm 1, plant 1. It's the number of units of capital in place, which is fixed at 25, times the cost of capital fixed at 1 per unit. So that makes 25, plus the wage rate equal to 1, and the amount of labor that we need for production, well, as a function of output, that is Q1 squared divided by 25. Similarly, we can determine the short-run cost at plant 2, which gives us 100 plus Q2 squared divided by 100. And then the total short-run cost function is the sum of the cost at the two firms, and just aggregating gives us 125 plus Q1 squared over 25 plus Q2 squared over 100. And of course, we cannot lump these two things together because Q1 may be different from Q2. And what is left for us to do is the most important thing, to determine the optimal levels of Q1 and Q2. Now, how to do that? Here we use our good old Lagrangian. So we want to optimize, maximize, or minimize something. In this case, we want to minimize our short-term cost, and we want to attain a certain production level. So that is the constraint. So the Lagrangian here is identical to the objective, minimizing the short run cost, given the constraint that we want to attain a certain production level Q, and it has to happen in either firm 1 or firm 2. So Q1 plus Q2 has to sum up to Q. Okay, so taking the derivative, because what we can determine is Q1 and Q2. These are the variables that we can tune as an enterprising entrepreneur. So we take the derivative with respect to Q1 and Q2, and we get two expressions with two unknowns. So we can solve this one for Q1 and Q2. Yeah, so actually it's two equations with three unknowns, but we can get rid of the lambda over here, and we get an expression of Q1 in terms of Q2. And this tells us that the production at plant 2 is 4 times the production at firm 1 in equilibrium. And we use that information and plug it into our constraint. So yeah, doing that, we get the total production. So let me see. Yeah, so we're done with question A. So how should output be allocated between the two firms? We answered that. So the output at firm 2 should be 4 times the output at firm 1. So total output should be divided in a ratio 1 to 4. So continuing here and also addressing question B. So given that output is optimally allocated between two firms, calculate the short run total average and marginal cost curves. And what is the marginal cost of the 100th widget, of the 125th widget, and the 200th widget? Okay, so we know that total output is Q. It's the sum of Q1 and Q2. And the production at plant 2 at the optimum is 4 times the production of at plant 1. So we can replace the Q2 over here with 4 times Q1, and then we get 5 times Q1. So we know that if the total production is Q, then 1/5 of the production takes place in plant 1, and 4/5 takes place in plant 2. And this information we use to derive our short-term cost function, because now we can replace that over here. So we already had the short-term cost function, and that was the expression that we derived in question A. And now we simply insert these equations for Q1 and Q2 for Q1 and Q2 over here. So doing that and then simplifying, we arrive at a short-term cost function equal to 125 plus Q squared over 125. And this is what we want. So we want an expression in terms of total output, not output at the individual plants Q1 and Q2. So short run cost as a function of total output is equal to 125 plus Q squared over 125. Now, given that we have this expression, the rest easily follows. So the short-term marginal cost is equal to the derivative of this thing with respect to Q. It's a very simple derivative. So it's 2Q over 125. And the short-run average cost is the short-run cost divided by total output Q. So we divide this expression by Q, and we arrive at 125Q plus Q over 125. And then the short run marginal cost at the specific output of 100 widgets. Now we just plug in the 100 in the expression over here. We get 200 divided by 125, which is $1.60. If we instead plug in the value 125, we get a short run marginal cost of production at the 125th widget of $2. And if we insert the value of output 200, we get a short run marginal cost of 320. The exercise would not be complete without looking at the long-term cost function. So this is what we will do in question D. How should the entrepreneur allocate widget production between the two firms in the long run? Again, calculate the long run total, average and marginal cost curves for widget production. This might strike you as a difficult question and a lot of work. In the end, it's not a lot of work if you realize that here we have a Cobb-Douglas production function which is characterized by constant returns to scale. And what does it mean? It really doesn't mean on how you allocate the production between the two firms in the long run. In the long run, both capital and labor are flexible, and the returns to production do not increase or decrease if you produce more units at one particular plant. So the entrepreneur in the long run will be indifferent to produce at one location or both. So at both plants, the margin rate of technical substitution has to be equal to the ratio between the cost of labor and the cost of capital. So we have that the marginal productivity of labor over the marginal productivity of capital at plant 1 and plant 2 needs to be equal to the ratio W over V. Well, that ratio is simply equal to 1 because both V and W are equal to 1. So this needs to hold at both plants. We know the marginal productivity of labor at both plants. So this means that both in plant 1 and plant 2, in the long run, we need the same number of units as we have the number of units of capital. So inserting that again into the production function, so you can replace K1 with L1. So the output of plant 1, say, is identical in the long run to the square root of L1 times L1, because we apply the same number of units of capital as we have the number of units of labor. So that's L1 squared. Taking the square root of L1 squared is L1, and the same holds for firm 2 or plant 2. So the contingent demand for labor and capital in both plants equals the output level in the long run. So it means that the cost function is equal to 2 times Q. And knowing that, it's very simple to derive the average cost function because it's 2Q divided by Q, and the marginal cost function is 2Q, and then taking the derivative with respect to Q, which also happens to be 2. So the average cost of production of widgets and the marginal cost of production of widgets in the long run is constant and equal to 2. And this is what you would expect because the Cobb-Douglas function is a constant returns to scale production function. So you want that the average cost is constant. And that completes exercise 10.5. Well, in fact, there's one short thing to add, and that is question D. How would our answers to part C about the long run total average and marginal cost curve change if both firms did not exhibit constant returns to scale but diminishing returns to scale? So the more you produce, the less effective it becomes. Well, in exercise 3, we found that it doesn't matter how you allocate the production over the two plants, but if there's diminishing returns to scale, then you want to do things differently. And how do you want to think differently? Well, you want to split output evenly across the two locations if there's decreasing returns to scale. So you can also ask what would happen if you have increasing returns to scale. So the more capital and labor you have in place, the higher the multiplication factor for your production. If you have increasing returns to scale within a plant, then you want to produce as much as possible within one plant. So in that case, you would allocate all production to one plant. But if the returns to scale are decreasing, then you will find that the average cost and the marginal cost are no longer constant in Q, but they are increasing in the amount of widgets that you produce. And this indeed completes exercise 2.10.5.